We keep expanding our knowledge of circular motion to the space, and today we will talk about satellites and weightlessness. So first of all, let's start with satellites. So on this, we'll know that Earth has a satellite, Moon is a satellite, and also it has a bunch of artificial satellites. So they are put into orbit by accelerating it to sufficiently high speed, but not too high, because if its speed is too high, then the satellite is going to escape from Earth. And depending on the speed, the satellite is going to have either a circular orbit or an elliptical orbit. Those are the most typical orbits, just around the Earth. Now, sometimes people ask why what keeps a satellite up, right? Why wouldn't it fall? Well, the answer actually it is falling towards Earth, but because the speed is too high, it just doesn't. It never falls. So in other words, if the satellite stopped moving, it would just fall directly on Earth. Plop, that's it. But if the speed was too high, then the satellite would go into the space. So you can see here is the path without gravity, and then with gravity, it's continuously being attached to Earth, or attracted to Earth. So it's like what we did in our very first lesson when we had something, an object, a ball spinning around us, right? We saw that the acceleration, the centripetal acceleration, is pointing towards the center. So kind of like same thing here, the satellite, the acceleration is pointing towards the center of Earth. So in other words, again, a satellite is falling towards Earth, but because of the speed, it does not hit the Earth. Same thing with the planes. Why do planes fly? Same thing. The planes technically falling towards Earth, but not quite. And then they eventually they land. So for the satellites, we're going to look at the satellites that move in a circle. So if they move in a circle, we can say that the acceleration is the centripetal acceleration, which we remember is v squared over r. So centripetal acceleration is v squared over r. And the force that gives a satellite the acceleration is the force of gravity exerted by the Earth. And because a satellite may be at a considerable distance from Earth, we will use Newton's law of universal gravitation that we discussed in class. And we are going to have an equation that looks like this. So G m, then mass of the Earth over r squared has to be equal ma, and then instead of a, we are using our v squared over r. So m is the mass of the satellite, and then me is the mass of Earth. R is the distance from the center of the Earth to our satellite, so that's going to be r. Okay, that was totally straight line. So that is r. And there is only one force that is acting on the satellite, and that is, yeah, and as I mentioned, r is the sum, it's the distance from satellite, it's the distance from satellite to the center of the Earth, or distance to satellite from the center of the Earth. So r is going to be actually equal radius of the Earth plus the height of the satellite above the surface of the Earth. Now, if we solve this equation for velocity, what we can see is that the masses are going to cancel out. So actually, it doesn't matter what mass of the satellite is. I believe we can also cancel one of the r's here. So now v squared is going to be equal g and then mass of the Earth over the radius, and then to find v by itself, we just have to calculate the square root of that. So square root of g m e over r. All right, so that is our equation for the velocity. Nice. So let's take a look at an example, a couple of examples here. The first example is coming up. Before we actually move on to our example, another thing that we should mention is that a satellite speed, as we can see, does not depend on the mass of the satellite. So we know that there are several satellites orbiting around the Earth. They might have different masses, but they will have the same speed and the same period. Okay, now this example, geosynchronous satellite. So a geosynchronous satellite is the one that stays above the same point on the Earth. And that is only possible if it is above the point on the equator, because the center has to be the center of a satellite is always at the center of the Earth, right? And if the satellite is not moving along the equator, is not above the equator, it's going to just move like whatever in a weird way. So it's not going to be staying in the same place, versus if it is above the equator, then it just turns with the Earth, right? So it's falling, it's moving, but the Earth is also moving as well. Um, so the questions are: determine the height above the Earth's surface of such a satellite. And part B, find the satellite speed. And part C, compare to the speed of a satellite orbiting 200 kilometers above the Earth's surface. So for our solution, we are going to use our formula again, m satellite times mass of the Earth over r squared, and it has to be equal, like in our previous example, mass of the satellite v squared over r. So that is our part A. Now in this equation we have two unknowns. We have r and then we have v. We know the mass of the Earth. We can see that mass of the satellite will cancel out. We do know g. But we remember that one full period of rotation is 24 hours, right? The Earth rotates in 24 hours, which means that the speed of the satellite has to be 2 pi r over t, where t is 1 day, 24 hours. I'm going to put it here. T is 1 day, which is equal to 24 hours. And then we know that it is 3,600 seconds per hour. So that is 86,400 seconds. So that is the period. Okay, let's plug it instead of V. So we have now masses of the satellite canceled out. We already saw that. So we have ME over r squared equals v squared is going to be 4 pi squared r squared over t squared, and then we had this r as well, right? Let's see if we can cancel anything else. Oh, we can cancel this r with one of those r's. And then now we are going to find, what do we have? We can find radius. We can find, right, the height above the Earth's surface. That's what we're looking for. So we can, well, cross multiply, simplify. Let's do that. So I'm going to cross multiply GME times t squared. So I'm multiplying both sides by t squared equals 4 pi squared, and then r times r squared is going to give me r cube. So now I can figure out r cube, which is g mass of the Earth t squared divided by 4 pi squared. And now all I have to do is I just have to plug in the numbers. So I have my 667 times 10 to the negative 11 Newton meters squared over kilogram squared, multiplying it by the mass of the Earth, which is 598 times 10 to the power 24 kilograms. Okay, that 4 looks like a 7. Let me fix that. 10 to the power 24 kilograms times t squared in seconds, 86,400 seconds squared, divided by 4 pi squared. Right? All that divided by 4 pi squared. If you have a calculator, you can pause and try to calculate. And if you don't have a calculator, you will have to trust me on this. R cube is going to be equal 754 times 10 to the power 22 meters cube. But that is R cube. We need to figure out R, so we calculate the cube root of this number, and then that is going to give us that radius has to be equal 422 times 10 to the power 7 meters. So that is the radius, but that, remember, that is the distance from the center of the Earth to the satellite. Yeah, and we need to subtract, because the question was how high is the satellite above the Earth. So we need to now subtract from this number 6,000, the radius of the Earth, 6,380 kilometers. Actually, let me erase. So that's going to be h equals 422 times 10 to the power 7 meters minus 6,380 kilometers times 10 to the third meters. And we are going to get approximately 36,000 kilometers. So that is about 6 radii of the Earth, above the Earth's surface. So that was part A. Part B. What is the satellite speed? We already saw the equation for the speed, 2 pi r over t, so we can plug in the radius and calculate, or we can plug the speed into this equation that we had before. So either one of them. I'm going to use the second one because it looks cool. It has a square root. G m e over r. So that's a square root of 667 times 10 to the negative 11 Newton meters squared over kilogram squared times mass of the Earth, which was 598 times 10 to the power 24 kilogram, all over radius, which is 422 times 10 to the power 7 meters. Remember, we are looking for the radius, the distance from the center of the Earth to the satellite. And then once we calculate this, so same thing, you can pause, you can try to calculate it on the calculator. And when you unpause, you should get 3,070 meters per second. Sorry. Meters per second. All right. And then finally, meters per second. Just so that you have an idea how fast it is, that is about 1,000. It's the same thing as 1,000 kilometers per hour. And it is about the same as 7,000 miles per hour. Okay, compare with the speed of the car, how the car is moving. If you're speeding, it's 70 miles per hour, so it's 100 times more, 100 times faster than that. Okay, part C is asking us, let's go back to take a look at part C. So part C says, compared to the speed of a satellite orbiting 200 kilometers above Earth's surface. So that means that the radius is going to be now radius of the Earth plus 200 kilometers. Radius of the Earth is 6,380 plus 200, and we are getting 6,580 kilometers. So we know that V is proportional to the square root of 1 over r. Right, from here. So V is proportional to the square root of 1 over r. And the coefficient here is g times me, that doesn't change. So what we can say is that the second velocity is going to be the same as what we just found, times square root of r over the second radius, the one that we found. I'm going to call it r2. All right, and then we just plug in what we got. So we got 3070 meters per second, and then we have our 42.2 kilometers. I converted this one for 22 times 10 to the power 7 meters. That's 42,200 kilometers. And dividing it by the new radius that we got, 6,580. And that is going to give us 7770 meters per second, which is approximately 28,000 kilometers per hour, which is approximately 17,000 miles per hour. So that's our question. All right, next part is weightlessness. So let's talk about weightlessness, apparent weightlessness. So on the satellite, we know that people experience apparent weightlessness. So we are going to, before looking at the satellite, we're going to look at the simpler case. We're going to look at an elevator. What is happening in the elevator? So over here, what I have is a lady with a box or a book, who knows, and there is some weight hanging on the scale, and the acceleration is zero. So the elevator is not moving anywhere. So that means that the forces, so let's take a look at this bag. So the forces acting on this bag are going to be force of gravity, mg, and the counter force is going to be the weight. So because there is no acceleration, no other forces, they have to be equal to each other. So weight has to be equal mg because acceleration is zero, right? So we can say that w, that was supposed to say w here. Okay. W minus mg has to be equal ma. But if acceleration is zero, so I have w minus mg equals zero, which means that w equals mg. Right? So that is the first case scenario when acceleration is zero. So the second case is when the elevator is now moving. It's moving with the up acceleration. Acceleration is, the direction of the acceleration is up. And what we see here is that, well, let's take a look at what happens with the weight, right? We still have the same equation. Weight minus mg has to be equal ma, but the acceleration now is acceleration. We have an acceleration. So that means that weight is going to be equal mg plus ma. And then a, if a is upward, then we add an acceleration, and that means that on the scale is going to read more than the actual read more than mg. So this weight is going to be called an apparent weight. Apparent weight of the bag, and in this case it's greater than the actual weight. If the acceleration was downward, then the apparent weight would be less than, because ma would be facing the other way, the other direction. Now here's an example. On this diagram you can see that, for example, a equals 1/2 g. So what happens in this case, then the weight is going to be equal mg plus m times 1/2 g. So we end up with 3/2 mg. So that's what we see over here. Weight is 3/2 mg, which means that the scale is going to read more, 1.5 times more than the actual weight of the bag. And now let's take a look at the third example. All right, this is our third example. Oh no, look at this. The cable broke and the elevator is falling down. What is happening? Well, when the elevator is falling down, then the acceleration is going to be equal g, and it faces down. So in other words, we can say a equals negative g, and our equation for the weight becomes mg minus mg, which is a zero. So that means, look at this, the scale reads that the weight of the bag is zero, the weight of the lady is zero, and then if she lets go of a box, the box is not going to fall, it's going to be floating right in front of the lady. Well, I mean, it's falling all right, but the lady is also falling, everything is falling. So within that cabin, elevator cabin, it looks like nothing is falling. They will experience weightlessness. We call that apparent weightlessness. apparent weightlessness, because it is a different a reference frame of the person, um, and for the reference frame of the person, the objects are not falling. However, the gravity is still there, and gravity, well, the gravity, the weight is still mg. Okay, but it looks like we don't. Um, they don't have it. Now, if there are people on satellite orbit, then it's a very similar situation to this, because remember the satellite, it keeps falling on Earth, so that's exactly what they experience. That's why you see all those pictures when the objects are just like flying there freely. Um, now, because okay, I'm back. So on the satellite, as I said, because the satellite is falling, the frame of reference of the satellite is apparent weightlessness, but the force of gravity still acts on the satellite. So the satellite is, as I said like 5 million times already, is still kind of like falling. However, if a spacecraft was out in outer space, away from the celestial bodies, away from Earth and Moon and Sun and like other attracting for other attracting bodies, so then in that case, the force of gravity would be very, very tiny, right? Remember, the force is inversely proportional to r squared. So the bigger the distance away from those celestial bodies, the smaller the force. So in that case, the person in this spacecraft would experience the what we call the real weightlessness. On Earth, people sometimes experience weightlessness. We also, well, if you saw a ballerina in the ballet jumping, or a skier jumping, or a snowboarder, right? Or like there are some with a parkour. Those people, when they jump for those like teeny tiny fraction of a second, those people experience weightlessness when they are falling and then they fall. Yeah. So that is it for our lesson today. I hope you enjoyed it. Give me a like, follow, subscribe. I don't know, whatever, all of the above. All right. See you guys. Bye.